So in the last lesson, we derived the geodesic equations for the Schwarzschild spacetime. Oops, I didn't write the word spacetime here. Of the Schwarzschild spacetime. And the Schwarzschild spacetime, of course, was based on the Schwarzschild metric, g mu nu, which we took as an ansatz, meaning it was given to us, and from that we calculated all of the connection coefficients, and then from the connection coefficients and the equation for the metric connection, we developed all of these coefficients that show up in these expressions, which these are just the connection coefficients multiplied by the appropriate functions, or time derivatives of the appropriate functions, but they're also first derivatives of the metric tensor components. We did all that the last time. So now we're going to start thinking about solving these equations. And you can see that this is a very difficult thing. At first light it is, but this is true of almost every physics course you take. You create a model and you work up the differential equations that solve the model, and then you look at it and you go, oh my God. And then the textbook systematically teaches you how to maneuver these expressions, simplify things, gather some terms, make a few reasonable assumptions, and then all of a sudden you end up with differential equations that are famous, like, you know, the Legendre differential equation, or Laguerre's differential equation that gives you Laguerre polynomials, or, you know, some differential equation that gives you the Airy function, or some known mathematical function. And that's exactly what's going to happen here. We're going to make a few assumptions and slowly whittle this down into something manageable. The difference is when we get to our manageable thing, it will be a function that you've probably not worked a lot with in your fundamental physics class. Even your graduate physics classes probably didn't deal much with elliptic functions, which is ultimately where we're headed. So keeping these in reserve, let's begin. By reserve, I mean I'm going to keep these on this screen here, and then I will take them one by one into the next screen and start simplifying things. So we'll start with the third one. This is the theta equation. Now, the idea, remember, theta is still going to be understood and interpreted in spherical coordinates as, we can kind of think of this, the x-axis, the y-axis, the z-axis. This actually is the phi variable, the azimuthal variable, which goes from 0 to 2 pi. And then theta is this angle, which goes from, I think we're going to do minus pi to pi, right? I'm sorry, not minus pi to pi. We're going to do, well, it only goes from 0 to pi, right? So let me erase that. Actually, get this right. It's 0 to pi, right? Where this is theta here. So we consider our system is presumed to be spherically symmetric. And the reason we know that is because the metric that we've chosen, the Schwarzschild metric, was solved for perfect spherical symmetry. That means the problem has no distinctions between any directions in space. It may have a distinction here in what we're going to interpret as the radial variable, with the caveat that distances along this radial line are not simply the value of this radial variable anymore, because this metric complicates things when you measure distance in the Schwarzschild metric. However, theta and phi are exactly the same as in spherical coordinates, which means angular distances, or distances on a sphere or on the surface of the sphere, will always be just like it would be in regular Euclidean system. We'll talk about that a little bit more when we derive the Schwarzschild metric. But the point I'm trying to make here is that no direction in space can possibly be favored in any way. And because of this, you can imagine that any object moving about the center will move in just a single plane cutting through the origin of your coordinate system. And it has no tendency to leave that plane and then enter, say, some different plane about the coordinate system. And because of that, we can then arbitrarily fix a plane and say that this free motion will just be established in one particular plane. And the plane we pick is the plane defined by theta equals pi over 2, which of course is going to be this plane here in all the quadrants. It's going to be the equatorial plane. Now, equatorial plane doesn't mean much because if you're dealing with a star, right, usually you say, okay, the equator is the plane that is perpendicular to the star's rotation, but there's no rotation in this star. So all possible choices are completely arbitrary. So we pick an arbitrary, completely general, without losing any generality, we can pick an arbitrary axis, and then from that axis we can establish a coordinate system, which includes this theta variable, and then we say, okay, we're going to live and work entirely in the plane theta equals pi over 2. So, and we know that will never change because an object will have, there's no way a force could be generated in a perfectly spherically symmetrical system that would lift you out of any given plane. If you did, there would be a preferred direction, and somehow there's no way a preferred direction could emerge. So we've already solved one of the 4 geodesic equations in a sense, just based on the spherical symmetry of the project, of the problem. So we are going to stipulate that the latitudinal angle variable is equal to pi over 2, and it's a constant. It's a constant. And so right away when we make that decision, we know that if it's a constant, its time derivative is 0, so this term goes away. Its second time derivative is certainly 0, so that term goes away. And the value of this term equals 1, and the value of that term equals 0, so that term goes away. And this just leaves us with 0 equals 0. So basically this geodesic equation is completely eliminated by this, I want to say it's an assumption, but it's not an assumption because we're not adding anything to the problem. The spherical symmetry allows us to make this choice. We don't lose any generality by making that presumption. So that solves the problem for this one, but what about these other ones? Well, certainly it's going to have an effect. That choice is going to have an effect in these other equations as well. So let's start examining these other equations. This is the radial equation, and let's see, in the radial equation, if we set our constant equal to 0, this term will go away, right? But it doesn't affect this term, and it doesn't affect this term. This term, that sign squared, it becomes 1, right? So this term, that part goes away and just becomes 1. So that simplifies that equation quite a bit. I mean, it significantly, simplifies it. What about the others? Well, here's the time derivative equation, and this one won't get simplified at all. There is no place to apply the theta equation here. Our theta equals pi over 2 equation doesn't affect this at all. And here is the azimuthal equation, the phi equation, and this one will be simplified. This one will be simplified somewhat, well, I don't know how significantly, but for pi over 2, the cotangent for pi over 2, that's going to be cosine pi over 2 divided by sine pi over 2, which is going to be 0 over 1. So I guess this term goes away entirely. Well, it goes away anyway because of the phi dot, right? So we just end up with, yeah, this whole thing goes away. So we're left with the part on the left, 2 over rho dot phi dot. Okay, so we've basically made one set of simplifications already. That's we've pretty fully exploited. We've fully exploited the theta of lambda equals pi over 2 ansatz that's established by the spherical symmetry. What next? Well, the next simplification is the insight that, well, let me rewrite this equation because the next simplification involves this equation in its form that's been reduced through this presumption. Well, we'll take this equation, we'll divide both sides by phi dot. So we'll get phi double dot over phi dot plus 2 over, well, let's not do 2 over, let's just say 2 times rho dot over rho equals 0. And what's nice about this is we can exploit the idea of the logarithmic derivative. The logarithmic derivative, we have a derivative of something over something, the derivative of something over the something. So that is what a logarithmic derivative actually is. So I'm going to rewrite this as the log, whoops, not the log, that's a 0. The derivative with respect to lambda of the log of phi dot, right, plus the log, plus 2 times the log of rho, right, which is also, I guess you could also write that as plus the log of rho squared. So it's the derivative with respect to lambda of this, right? But that equals 0. So now we know that if that equals 0, we know that if we integrate this, we get a constant, right? So we know that the log of phi dot plus the log of rho squared equals a constant, and we'll call that constant little h. But the sum of the logs, of course, is the log of the product. So that's the log of phi dot rho squared equals h, right? And then if I just raise both sides to, if I just take the exponential of both sides, I get phi dot rho squared equals e to the h. Now, the truth is I want phi dot rho squared to equal h, so I introduced this constant too soon. I should have done it this way. I should have introduced not h, but I should have said a constant. And then I should have said a constant. And then this is e to some constant, and we'll call that h, right? That's what I meant. So, but the bottom line is the rule that this differential equation gives us is this. We have this constant is true. Phi dot rho squared is this constant h. It's not Planck's constant, which I don't even know how I would write Planck's constant, something like that, I guess. So this is an important fact. This is called a constant of the motion. That is this product. So understanding what this means literally is phi and rho are functions of lambda, right? So phi as a function of lambda, its first derivative with respect to lambda, times rho, which is a function of lambda squared, that product is always going to equal h, and that's going to help us a lot. So that's a full exploitation of this geodesic equation. Okay, so with that in mind, what next? Well, if we look at this, we think we can almost pull the same trick. We can divide through by t, and we'll get t double dot over t dot, and then we'll have a rho dot over some function of rho. So maybe we can make some progress on that. So the first change is this, right? We divide through by t dot, and now we have to kind of work at this. This is going to be the logarithmic derivative of t dot. So that's easy. So we can actually write that already by just saying d by d lambda ln. Oops. There's only one thing to the right. You don't need parentheses. But then the question is what do we have over here? What do we have next? Well, the answer is we have the log of 1 minus alpha over rho equals 0. Oops, now I've got my bracket problem that I had before, right? This is a 1, alpha over rho. You put parentheses here, and then you close the brackets. Okay, so how do we know? Well, d by d lambda of ln 1 minus alpha over rho is, the derivative of the log is 1 over 1 minus alpha over rho times the derivative of the inside, which is minus minus, which is plus alpha over rho squared rho dot, right? Which is going to equal alpha rho dot in the numerator, and then rho squared minus alpha rho in the denominator, which is alpha rho dot rho times rho minus alpha, which is a match, right? That's what this is. Alpha, oops. That's what this is. Alpha rho dot. So we did it correctly. So the derivative of this and the derivative of this is just a restatement of this, right? There's really no difference. When I write this down, I'm just rewriting this. It's just this in another form. But here, I now see that this, if I integrate both sides, this plus this log plus that log is going to be a constant. That is, integrating this is totally trivial, and you get this equals some constant. So we know we're on the hunt for a constant of the motion, so it's not hard now to do the same thing we did before. The log of t dot 1 minus alpha over rho, right? That log equals a constant, and then we end up with a time derivative of t times 1 minus alpha over rho. That equals a constant, and we'll call that constant kappa. Kappa. I mean, these are the same symbols I use in the book, Why Does It Move? So this is another constant of the motion. Remember, t, the time, is a function of lambda. This is an important point. I'll just keep stressing it every chance I get, right? Time is just another variable like space in general relativity. This world line parameter, lambda, tells us what time it is, right? We know how far, what the parameter value along the world line is, then I learn what the time is. Likewise, rho is also a function of lambda. The radial distance from the origin, the Schwarzschild radial distance from the origin, is a function of this world line parameter. So this is a functional relationship here. That's a first derivative of a function, and there's the first derivative, or there's a function itself in the denominator there. Alpha is a constant, k is a constant, and of course 1 is a constant. So this is another constant of the motion. So we've been able to simplify this expression quite a bit. Remember, we had to start, and this one we didn't have to use the theta equals pi over 2 ansatz to begin with. Okay, so what next can we do? Now you might think that our next step would be to go and attack the radial equation, right? But no, actually, it turns out that these two constants of the motion are so strong that we can actually proceed from there using the metric interval itself, and that's what we're going to do. So this is the metric, the line interval, right? This is the interval of length of space times path squared, and these are the metric components, just like we started this whole process in the last lecture. And what I've done is I'm now going to emphasize that this length is the proper time. It's the proper time. We're going to call this c squared times the proper time. Now, c squared in our units is 1. So every time you see a c squared, in our units you can think of it as being 1. The c squared appears here to convert that time into units of distance, right? C squared, t squared would be units of distance. So I'm going to pull out that c squared. And the reason I'm doing this is to emphasize that this length, this interval along the world line is going to be measured is going to be the proper time of the particle following the world line. And if I choose units where c squared equals 1, then that length will in fact be it'll be ds squared equals d tau squared, and s squared and tau squared are the same. But ultimately, this is a way of parameterizing everything based on the proper time. And by putting in the c squared here, you can get a little bit of emphasis on that, but immediately we're going to put c squared equals 1 right back into the expression. So this is the unit interval. But if I divide everything by d tau squared, then what I would end up getting is I would get c squared equals minus c squared 1 minus alpha over rho, and then here I have t prime squared, where t dot is dt d tau, which is the coordinate times change with respect to the proper time. Remember, this proper time is developed as the length of the world line. This is just a coordinate in the coordinate system of the Schwarzschild coordinate system, which is a different time. And t prime is this derivative, right? Because we're basically parameterizing the world line with tau. That's how this is working. So once we do this, we get this t prime squared, and then we get plus 1 minus alpha over rho to the negative 1, and then this becomes rho dot squared, same principle. Now this one here just goes away because d tau is 0, right? Because we're still assuming that phi of any parameterization is still pi over 2 constant. So that goes away. And this sine term here, that becomes 1. So this becomes, this becomes plus rho squared phi dot squared equals c. Notice that it equals c, because this is now what happens to the line interval if we take that derivative. So now with this we start seeing the power of the constants of the motion. Here's the two constants of the motion are here. This first one implies that phi dot equals h rho to the minus 2, and therefore phi dot squared is h squared rho to the minus 4. And then this one implies that t dot squared, let's see if I can just do it all at once, is kappa squared times 1 minus alpha over rho to the minus 2, right? So now I can take this and substitute it. Let's do it in red. I can take that and substitute it right there, and I can take that and substitute it right there, and that eliminates those two derivatives. And I'll only have, when it's all done, I will just have an equation that's a single derivative, or it'll be a nonlinear equation, but it'll only be in terms of rho, because here's rho, here's rho, here's rho. So what I'll have done is I've taken finally all of my, my geodesic equations. I eliminated one, I super simplified two, ignored the third one, but went back to the line element, which is always true, and used those differential equations to substitute into this line element expression and eliminate two of the three different variables in there. So I get a single differential equation for one function, the function of rho, and it'll ultimately end up being a differential equation seeking rho of lambda. So that sounds interesting. So let's complete that substitution. And this is the simplification. You know, I just noticed something. I should point this out. Because we're using the mostly minus or the mostly plus convention, right? Plus 1, plus 1, plus 1 for our signature. This, for any time-like geodesic, is always going to be negative. It's going to be less than 0. So I actually need a negative sign right there. So this should be a minus c squared, right? Because the paths in space-time in this convention always have time-like paths always have negative length, and we're interested in the time-like paths for right now, at least. So that should go right there. Okay, so so now I've made the substitution, and I've given you just what I promised, right? This is now all you see are rows, row, 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 and this can simplify to 1 over rho squared. So ultimately, when we manipulate this a little bit more, we can get it into a most simple form, most reasonable simple form. And let me do that. All right, so we'll simplify this first part. That's minus c squared equals minus c squared kappa squared divided by 1 minus alpha over rho, because this is in the denominator with 2 factors, and that's in the numerator with 1. And then it's plus, let's say 1 over 1 minus alpha over rho dot squared, and then plus h squared over rho squared. All right, then why don't I, okay. And then we multiply by this denominator, I guess, to clear it out. And I'll get minus c squared 1 minus alpha over rho equals minus c squared k squared plus rho dot squared plus h squared over rho squared times 1 minus alpha over rho. Let me clean this up a bit before it messes me up. Equals minus, that's nothing there. And I know that the final form, I want this rho to be on the far left, so I'm going to go rho dot squared, then terms with rho in it would be plus h squared over rho squared 1 minus alpha over rho, and then minus c squared kappa squared minus c squared 1 minus alpha over rho equals 0. But we don't want to have our function sort of mixed in with all these constants. We kind of want to have first derivatives, no derivatives, and then constants, right? That's how differential equations look best. So we will write rho dot squared plus h squared over rho squared 1 minus alpha over rho. And then I want to go plus c squared alpha over rho, and then minus c squared kappa squared minus c squared equals 0. And then this part should just end up being minus c squared kappa squared minus 1. Right, so why don't I just do that? Minus c squared kappa squared minus 1. Minus c squared kappa squared minus 1. Wait a minute, something's not right here. Hold on. When I took this over here, it's a minus sign over here, so it should be a plus sign on this side, right? So I think I need to go with a plus sign here, right? Which makes this now that becomes if that's a plus sign, then this c squared that becomes a minus sign here, right? So that becomes a minus sign like that, and then does that change anything else? And this becomes minus c squared kappa squared plus 1. Yeah. Let me get that right. So this now becomes a minus c squared kappa squared plus c squared, which is minus, if you pull out a minus c squared, you get minus c squared kappa squared minus 1, right? If I were to expand that through, I'd get a minus c squared kappa squared and a minus c squared, which is a plus c squared. So you get this expression here. So, and that's what I want right up there, right? So I'll move it right there. Phew. Okay, so this here is a differential equation for phi of lambda. It's an ordinary differential equation for phi of lambda, right? This first one here is d phi, what do I mean phi? Rho of lambda, d rho d lambda squared. So it's a nonlinear differential equation because this guy's coming in as the square of a derivative, right? So this is an ordinary differential equation, but it's nonlinear. Also, it's got rho in all these weird places. It's got rho, and it's got a cubic rho in the denominator here, right? A square rho in the denominator there, a linear rho in the denominator there, and then this is a constant. Now, you may remember from probably advanced electromagnetic theory, you ran into differential equations that had the dependent variable in the denominator. And there was this substitution where u equals 1 over rho, and sure enough, we're going to do that in this case as well. So if we were to solve this, now because of the way we've done our substitutions up here, and by the way, we can turn c squared into 1 whenever we wish. I just left it there so we could remember that we're parameterizing this with the proper time. D tau c d tau equals ds, right? Where this is the path length along the world line, and this is the proper time. This is that path length sort of broken up into the proper time. So with that in mind, this is the proper time. So if we solved this, we would get a function of the proper time. So if I had a clock, this is the world line, and this particle is along the world line, and it has its own little perfect clock. If it just checks its clock, and then it takes that time and runs it through this function, it'll know exactly how far it is radially in Schwarzschild radial units, how far it is. Well, I shouldn't say how far it is. It takes a little more to know how far you are from the center, but you will know your Schwarzschild radial coordinate for any moment of time on your clock as you move through this world line. So that's something, right? It's not everything because we still don't know, well, we do know that you're at pi over 2, right? But we don't know your azimuth, right? Because really what's going on is, here's the center of the coordinate system. You've got some motion. That motion has a phi coordinate, right, off of some reference 0. So that coordinate has some phi coordinate, and it has a radial distance, or a radial coordinate r. Now, we'll be able to tell you this radial coordinate with respect to the clock on the particle that's moving along this world line. But we still don't have a way of determining the phi, your phi angle. So, regardless, this is the equation you would have to solve if you wanted this thing. And it does not look easy, does it? The problem with this is despite the fact that we have a differential equation for this, which would give us this nice answer to at least one of the coordinates of the motion, it's kind of a bear to solve. And what we're actually going to try to do is we're going to try to find a different expression. We're going to try to find phi as a function of the azimuthal angle. So if you tell me the azimuthal angle that you're at, say it's 30 degrees, or we'll probably use radians eventually, but say it was 30 degrees, I can take that 30 degrees, put it into this function, and then I can tell you how far you are from the center. So it doesn't tell me anything about the time that this path is swept out, but it does give me a connection between the radial distance and the azimuthal distance. It turns out it's actually a lot easier to solve for that than it is to solve this guy, this nonlinear equation for the time. They can both be done, but we're actually going to work on this one first. All right, so let's see how that's done. All right, so the first thing to remember is that in this equation, rho dot is d rho d tau, with the derivative of rho with respect to the proper time. And using the chain rule, that is simply d rho d phi, multiplied by d phi d tau. Now, d phi d tau we actually know, and we know that from the constant of the motion. We know that from this expression here. That is d phi d, whatever the parameter is, which is in this case tau, rho squared equals h. So d phi d tau equals h over rho squared. So we are going to write this as, let's see, as h over rho squared d rho d phi, right? So everywhere I see a rho dot, I can substitute this, h squared over rho phi. And that's a start, right? So I see a rho dot here in the beginning. So I will go and I'll make that substitution. And this is after expanding this, the only real substitution is here in this first term. That's the only place where you see a rho dot. But I've expanded these other terms. So I have this term, then h squared over rho squared, h squared alpha over rho cubed, c squared alpha over rho. Now remember, so let's make our substitution c equals 1. Right? If c equals 1, then we know that we know alpha is measured in distance at that time, because that's our units when c is 1. So this becomes unitless. This becomes unitless. This becomes unitless here. This is h squared alpha over rho cubed. So h is also measured in units of distance. H squared is measured in units of distance. So this becomes unitless. This becomes unitless. And then this is measured in units of, let's see, this guy here. It's also, kappa is also, when c equals 1, is also unitless. We actually probably should go back and probably point that out. Here where we created, where did we create kappa? We created kappa here. Right, so if we think about this in terms of when rho is very, very large, right? Imagine rho is extremely big, so this term goes away. And then we have t dot equals kappa. Well, that's the same thing as saying dt d tau equals kappa, and then dt equals kappa d tau, and that, this is measured in distance, that's measured in distance, so kappa is actually unitless. So this differential equation is now what we have to work with, and it can be further simplified, presumably by multiplying by rho to the fourth, right? That'll get rid of this power of 4 in the denominator here. It'll put a square power there, a linear power there, a third power there, right? And then a fourth power over here by the constants. Oops, I forgot a square here, obviously. It's an important square, otherwise it's not nonlinear. Well, it would still be nonlinear, but that square is important. All right, so by my calculation, I end up with this expression, which is our derivative squared. Then I have these two fourth power terms that come from these two constants. And then a second power term, which comes from this by multiplying through by rho to the fourth. you cancel the denominator, leave 2 powers of rho in the numerator, and you have h squared canceling with the h squared, so you just have a naked rho squared. Then this minus alpha rho comes from this term, where that cancels with this, and this comes up there, and it leaves 1 power of rho. And then this c alpha rho to the third, that comes from this term here. C squared alpha stays there, h squared goes in the denominator, 1 factor of rho cancels, and then you end up with this expression here. But that can still be tightened up a little bit. And we'll do that. And this is our next form of the equation, which, look, we can clean this. I mean, we can, I should have just set c equal to 1, so I'll do that, right, and basically get rid of those things, right? And if I want alpha equal 2m, right, 2 times the mass, where if I set g equal to 1, alpha is 2m. And there are versions of this equation floating around out there where you'll see a 2m substituted for alpha in both of these spots. But we will not be doing that. We'll leave alpha as its own little constant. And this is called the radius anomaly equation. And anomaly is not meant something to be unusual, but it's when you have an orbit, an elliptical orbit, the anomaly of that orbit is one of these angles. So if your planet is here and there's some sort of elliptical orbit, let me draw this a little better. If your planet is here and you have an elliptical orbit around the planet, I'll exaggerate it. So the planet is at one of the loci of the orbit. Then you draw a line to the nearest point of approach, and if the object is, say, there, then this angle here, phi, it's called the true anomaly. I don't know why, I'm not an astronomer, but they call that the true anomaly, the true anomaly. This distance here is called the periapsis. The distance here to the faraway point of the ellipse is called the apoapsis. And then, of course, the shape of this ellipse has some eccentricity, and there's a whole bunch of different there's a whole bunch of different notations. But it's called the true anomaly. So this is the radius anomaly equation. It is presumably the radius as a function of the anomaly, where this is our gravitating star. This is some orbit around the star, which we're presuming for now is elliptical, but we don't know that. I mean, this certainly isn't this isn't going to have conic functions as the result. This is not going to solve to be parabolas and ellipses like your regular inverse square law in mechanics will. But we're going to borrow all of these language. So we still have this radius anomaly equation, and this is it. All right, so I think that's all for this lesson. This is a big step. We've gotten all the way to a differential equation, a nonlinear differential equation that looks like it's going to be a real piece of work to solve, but it will give us something interesting about an actual orbit in the space-time, in the Schwarzschild space-time. So we're excited to start working on it, but we really do have to attack it in many different ways, and that'll take a few more lessons to go. But we'll stop for now. The next thing when we do start working on this, we're going to start manipulating these variables, turning things into dimensionless units, and we're going to really take this formula into a very, very abstract world where we can actually apply mathematical special function theory to it. Right now it's a little bit too specific. We got to really bang it into shape so we can take it to books like Gradstein and Rezdak, or or Bronovitz and Stengun, all those famous mathematics texts that just are full of formulas. we got to get it into that form so we can take it to those texts and come up with some answers, because God knows we're not going to solve these differential equations ourselves, nor should we. Some guys did that back in the late 1800s, so we're going to lean on their work. Okay, so we'll see you next time.